Okay, it's a pleasure to have Philip Griffiths here in the Institute. He's a legend in complex algebra and differential geometry. The work he has done during his life has been really deep and influenced all the field in algebra geometry. He received his PhD from Princeton in 1964 under the direction of Donald Spencer. He held positions in Berkeley, Princeton, Harvard, and Duke. He was also director of the Institute for Advanced Studies at Princeton. He has been a leader in algebra geometry and complex differential geometry. He has been awarded for several important prizes. One of them is the Wolf Prize, together with the Lena Mumford. He also received different kind of, I don't know how to say, prizes, awards, and things like that, because it has been very important. So the title today is going to talk about using Hodge theory to detect the structures of a compactified modular spaces.
Thank you. It's excuse me. It's a real pleasure to have the chance to be here at this opening conference for IMSA in Mexico City. I think it's a wonderful event, and we can, I hope, look forward to many more similar events here or elsewhere in the region, and also back in Miami. The talk I'm going to give, I think I won't get through all of the overheads. They're on the IMSA website. It's in the Math Department at the University of Miami. It's dealing with a question in algebraic geometry, specifically with moduli. The moduli space for algebraic varieties of general type was shown to exist some years ago by Kolar, Shepard-Barron, and Alexeyev. For algebraic curves, this is a very classical story going back, well, beginning with Riemann, but especially beginning with Mumford and others in the 60s. The global moduli space of algebraic curves of a given genus is a very beautiful and well understood object. When you come to algebraic varieties of general type, which is similar to algebraic curves of genus 2 or more, then the picture is quite different. Kolar, Shepard-Barron, Alexeyev proved the existence, but so far as I know, there's no known example where the global structure of the moduli space has been worked out. One of the tools, early tools, and very instrumental tools for algebraic curves was Hodge theory. And so what this talk will be about is really the beginnings of how one might use some aspects of Hodge theory to study moduli of algebraic surfaces and to illustrate how for one particular algebraic surface, sort of the analog of algebraic curves of genus 2, the first ones you come to after genus 0, the Riemann sphere, genus 1, elliptic curves. The analog of that are called I-surfaces, and there's beginning to emerge, using Hodge theory, a fairly complete picture of what the moduli space looks like. So that will be, I think, the general goal of this talk is to just explain the terms and at the end give the illustration of this one particular algebraic surface. To state the problem, and some of these terms will be defined in the talk, the cohomology of a smooth variety, projective variety, carries a very rich structure, a Hodge structure. And the space of, it's a linear algebra object, the space of all such Hodge structures forms what's called a period domain. And if you have a moduli space, taking the Hodge structure on the corresponding smooth projective variety gives you what's called a period map. Classically, this goes back to Riemann, even before Riemann, one thinks of the integrals of differentials of the first kind on a compact Riemann surface. That matrix is the period matrix. This is some extension of that to higher dimensions. And the period mapping then associates to the moduli space, so family of varieties parameterized by M. The period mapping gives an invariant of the moduli space, and there is a canonical extension of this mapping. One studies moduli frequently by looking at how smooth varieties degenerate. The boundary of moduli is in many ways much more intricate, even interesting, than the sort of smooth part. And classically, one knows to study many questions in algebraic geometry. You can best get at them by degenerating the variety to something singular, which is simpler in some respects, and for that way read off what the structure of the original variety might be. So here there's a canonical extension of the compactified moduli space. This is not yet proved to be what you expect it to be, a projective variety, but it has all the properties as far as this problem goes that one needs for that. So the stratification of this image is known by Lie theory, and the problem then is to what extent does the stratification of the image of this extended period map. So you're looking at the Hodge structures in the limit as the varieties become singular, organizing those into strata. That's done by Lie theory. You want to know to what extent does that determine the stratification of the original moduli space. For a particular surface, you would want to know not only does it determine the stratification, but what do the strata look like? That is, what surfaces correspond to different strata? How do they fit together? How may one surface degenerate to another? And so forth. The stratification then of the moduli is by deformation type. So deformation can be here either of smooth varieties, which remain smooth, or of singular varieties, which deform in such a way that the singularities remain locally the same, so-called equisingular. That's how one would stratify moduli, including singular varieties. So one wants to know what surfaces occur on the boundary, what are their desingularizations, just how do they fit together? What is the picture, the global picture of the moduli space or a given type of algebraic surface? So that's the algebrogeometric side, the stratification, algebrogeometric stratification of moduli. On the Lie theory side, there are two types of subvarieties. So they're not exactly stratifications, but they behave as if they were, of this image of the exterior extended period mapping. One is by the different ways in which a Hodge structure can degenerate. That's done organized by Lie theory. It's a very interesting, very beautiful story. The other is if you just look at all the Hodge structures of a given type, some among those will have special features. For example, for elliptic curves, very particular elliptic curves have automorphisms, so-called complex multiplication. Okay? In general, in Hodge theory, among the space of all Hodge structures, there will be those where you have additional symmetries or additional Hodge tensors. That's the technical way of stating it. So that gives you sort of these subvarieties running through the space of Hodge structures, and those then would, if you like, if you think in terms of algebraic surfaces, those would correspond to algebraic surfaces that have additional geometric structure in them. They have additional Hodge classes, they have for surfaces, you think of them having a special configurations of curves, things of that kind. So that's how the Hodge, Hodge theory side looks. So one wants to know from moduli to Hodge theory, how much can you read off from that map, and what does the stratification on the Hodge theory side tell you about the algebro-geometric side? The example, simplest example, but it's a good one to keep in mind, is for moduli of curves, genus Riemann surfaces. For genus 2, this is the picture of the stratification of moduli. And the solid arrows reflect a degeneration in which there is non-trivial monodromy. Okay? Monodromy is the basic topological invariant. When a family of varieties becomes singular, you just take the family, so you think of it as a family of varieties over the disk. Over the origin, you have a singular one. You look at the topology, how that changes when you turn around the origin. What's the action of taking a cycle and going around the origin in this topological family? That's monodromy. It's the basic invariant of topological invariant of how you want to understand how an algebraic variety degenerates. So those are the solid arrows. The dotted arrows are the second type of sort of stratification of Hodge structures that I mentioned. Here, you're just acquiring, the Hodge structure is becoming reducible. So it gets an additional Hodge tensor, namely it just decomposes the Hodge structure into a sum of two. Okay, these are the ones with finite monodromy. And this picture will persevere in higher dimensions. We're going to see when you come to surfaces that it's very convenient to organize how the moduli looks according to whether the monodromy is of finite or infinite order. So for algebraic surfaces, we're going to discuss two types of results, sort of general results that are valid for any family of algebraic surfaces. And then for a particular I-surface, these are the ones that are regular. That means they have no holomorphic one forms. The first Betti number is 0. And they have two linearly independent holomorphic two forms. It's like a Riemann surface of genus 2. Okay? The canonical bundle should be ample. And I forgot to put it here, but the square of the canonical bundle, k squared, the first Chern class squared should be 1. That's the smallest possible number. So for these, there are going to be three types of results that come out. First, when you study singularities of algebraic varieties in curves and surfaces in higher dimensions, it's very convenient to organize those into Gorenstein and non-Gorenstein. Gorenstein ones are ones for which, if you like, the dualizing sheaf is a line bundle. They behave in many respects as if the variety were smooth. Duality is easy to use. Riemann rock seems to work in general the same way it does in the smooth case, and so on. And the non-Gorenstein ones. These are the ones which, well, they're not Gorenstein. And you don't have this distinction for curves. It only appears for surfaces. So the Gorenstein part of the moduli for this particular surface, I'll try to explain how that's completely captured by Hodge theory. The Hodge theory, you can say how that degenerates, and from that you can read back and see which surfaces are on the boundary, what the dimensions are of the moduli, or of surfaces of that type, so on. Okay. So that's really very much like the curve case, except the boundary is more elaborate because you have more different types of surfaces that can turn up. In a phenomenon not present in the curve case, Hodge theory provides a guide as to how to desingularize this moduli. I should have mentioned that the moduli space for curves is essentially smooth. It has sort of finite quotient singularities, but basically it's essentially smooth. For algebraic surfaces, much the opposite occurs. The boundary is highly singular, and the natural question is, how do you desingularize it? And there, Hodge theory will give you a guide as to what to do to desingularize it, what to try to do, and then you go back and use algebraic geometry to try to do that. And that's what will be done for this particular surface. And the non-Gorenstein part, that's very interesting. The first fact about the non-Gorenstein part is whenever a surface acquires a non-Gorenstein singularity, the monodromy is finite. It's a little result, it's a Hodge theoretic result, but what that means is that when the surface acquires the non-Gorenstein singularities, that even though the surface is becoming singular, since the monodromy is finite, there's a well-defined Hodge structure over the origin. It's as if even though the variety is becoming singular, the Hodge structure isn't. So, one wants to understand that and use that to help figure out what the non-Gorenstein singularities that can occur in moduli can be. For moduli, I'm just going to give an informal account of the story. Given a family of smooth varieties over the punctured disk, where the smooth ones are of general type. General type means that they have as many holomorphic differentials as is allowed just by the Riemann-Roch theorem. So it's like genus bigger than or equal to 2. They have a lot of multiple holomorphic differentials. One wants to define a unique limit. There are many limits, but you want to say, what is the unique one? And the result is, and this is the Kollard, Shepard-Barrett, Alexeyev one, that there is a unique completion where the total space has so-called canonical singularities. I'm not going to explain what these are, but they're the simplest types of singularities that you can get. And the relative dualizing sheaf is relatively ample. So think of that as even in the limit, the variety remains of general type, but where you're allowing your differentials to have some singularities. So a moduli space has a unique completion where, one says that then that a variety that has these properties that you use to fill in the origin is stable. Stable means that the canonical sheaf should be a Q Cartier. Some multiple should be a line bundle and it should be ample. These are so-called stable varieties. Those are the ones with good moduli theory. Well, moduli space has a unique completion where you add all the stable varieties of the given type. To prove that theorem, there are a number of quite intricate, highly technical aspects. I'm not going to get into those. As I say, the overheads are on the website, and there are references in the overheads to the literature that explains this. The second point, though, is for curves and surfaces, the singularities of a stable variety, you can list them. Not true in higher dimensions, but for curves and surfaces, they've been classified. For curves, that just means the curve has a node. It's just like those pictures that were drawn. For surfaces, it's convenient, as I said earlier, to organize into normal and non-normal, Gorenstein and non-Gorenstein. And this is just a comment about the non-Gorenstein ones. So the canonical, the Gorenstein canonical singularities break into two types. So let's just try to get some rough picture of what sort of singular surfaces we have to allow. The simplest ones are so-called canonical singularities. There's a vast literature on these. They're very classical. They were classified in the 30s by Duval. They're sometimes called Duval singularities or ADE singularities. Their classification is in terms of Dinkin diagrams. So one knows exactly what these singularities are and what their equations are. For example, the simplest one is just a surface that has an ordinary double point, a node. It's like the vertex of a cone. The desingularization, you just blow up the vertex and you get a curve which is contracted to the singular point on the cone. It's a Riemann sphere with self-intersection -2. The next type are what the singularity theorists use. This is their notation. These are quotient singularities. They're quotients of C2, or analytically, they're quotients of C2 by finite groups, as explained here. So for the non-Gorenstein ones, they should be Q-Gorenstein smoothable. That means that you should smooth them, keeping the Q-Gorenstein condition. And the only singularities that occur for stable surfaces are these quotient singularities of this type. There's very special ones. Or there are three other ones, sort of exceptional ones. So that's a list. You know what all the singularities are. Okay. What one doesn't know is what the global structure of the singular varieties are. For example, how many singularities of a given type can you have, and so on. The non-isolated ones, I'm not going to say much about those. They are discussed in those notes, and there's some references there to those. I'm going to focus more on the normal ones today. From Hodge theory, I'm just going to list the objects and say where those objects, how they arise geometrically. So a polarized Hodge structure of weight n, it's linear algebra data. It's given by Q vector space, a bilinear form, and a filtration on the complex vector space, decreasing Hodge filtration, satisfying this condition. A more familiar form of this condition is if you look at the intersection of FP with FQ bar, then the vector space has so-called Hodge decomposition. It decomposes into PQ parts with this conjugation relation. The way to think of that is on a complex manifold, the complex differential forms decompose into type according to how many DZIs and how many DZI bars there are in the differential form. P is the number of DZs, Q is the number of DZ bars. So the decomposition of differential forms descends to cohomology. That's the Hodge theorem, and gives a Hodge structure on cohomology. The variety is a projective variety. That gives it a so-called polarization, and that leads to bilinear forms satisfying the so-called Hodge-Riemann bilinear relations. So you have these bilinear forms, and you have the two Hodge-Riemann bilinear relations. We won't use those, so I won't explain what they are. The primary example is just a smooth projective variety, the cohomology. So when the variety moves, the Hodge structure will move with it. Topologically, it'll stay the same. Nearby varieties are homeomorphic. But the Hodge structure, so the cohomology as a Q vector space doesn't move. If you complexify it and look at how the Hodge decomposition varies, that is what one detects in these period mappings. A mixed Hodge structure, that's given by the data of the vector space and two filtrations, a weight filtration defined over Q, increasing, and the descending Hodge filtration defined over C. And the linear algebra condition is that on the associated graded successive quotients, the Hodge filtrations induce Hodge structures of weight K. So it's the successive extensions of Hodge structures. Sort of geometrically, you think of a variety, think of an algebraic curve with a singular point. Okay? Then the cohomology will have a mixed Hodge structure where the weight filtration reflects the cohomology of the singular point. That's a trivial thing in this case. And then the cohomology of the desingularization. In general, if you stratify a variety, if you'd use resolution of singularities to stratify the variety by so-called normal crossing varieties, smooth things, then the mixed Hodge structure is built up from the pure Hodge structure on smooth things by various exact sequences. When you go to studying degenerations of algebraic varieties, an additional linear algebra construction comes in. This comes out of monodromy. I'll explain that in a minute, but here you should be given a nilpotent endomorphism, and given a nilpotent endomorphism of a vector space, that gives a unique increasing filtration of length 2m, where m is the index of, or m plus 1, the index of nilpotency. And it should satisfy two conditions, that the n drops the weights by 2, and it gives an isomorphism of the stuff, the associated graded, the stuff above the middle to the stuff below the middle, so-called Hard-Lefschetz property. There's a unique weight filtration then associated to any nilpotent endomorphism with these properties. So a limiting mixed Hodge structure is a mixed Hodge structure with such a weight filtration and where the n drops the Hodge filtration index by 1. So it satisfies this additional condition. Period domains, that's just the set of given polarized Hodge structures with given dimensions of the HPQs. Here one begins with the classical case of Riemann surfaces of genus 1. The period domain is just the upper half plane. Okay, that's the ratio of the periods of the holomorphic differential on a Riemann surface of genus 1. And in general, a period domain is a homogeneous complex manifold with compact isotropy group. Among those are the special ones, the Hermitian symmetric ones, where the isotropy group is the maximal compact subgroup. That's the so-called classical case. These correspond to Hodge structures arising from algebraic curves and from K3 surfaces, and that's it. Anything else is non-classical. So this is the case weight 1, the so-called Siegel upper half plane, and weight 2, where the period domain is an orthogonal group, indefinite orthogonal group, divided by a unitary group cross an orthogonal group. Non-classical means that the A is at least 2. So you have SO4 something. The classical case where A is 1, those are K3s. The compact dual is the set of filtrations that satisfy Hodge-Riemann 1. Just forget the second Hodge-Riemann bilinear relation, which is an inequality. Just look at the first one. That's like looking at the upper half plane in the Riemann sphere. The reason you use that is in the limit, the Hodge filtrations are going to escape the period domain. They're going to leave the upper half plane and end up elsewhere in the Riemann sphere. Okay? So you need some place to receive what happens to the Hodge filtrations in the limit when an algebraic variety degenerates. I'm not going to need this, so I think I will skip that. So the example of a period mapping is when you have a family of smooth varieties and you just look at the polarized Hodge structure on the fibers, what was mentioned before. I'm not going to use the infinitesimal variation. For the limiting mixed Hodge structure, here one pictures a family of varieties over the disk, smooth except at the origin where you have some singular thing. You have monodromy. That's the effect of the fundamental group of the base acting on the cohomology of the fiber. And the monodromy theorem says that first any automorphism of a vector space decomposes into a semi-simple part and a unipotent part. So Jordan normal form. The monodromy theorem says the semi-simple part is a finite order. All the eigenvalues are roots of unity. And that the unipotent part has an index of unipotency less or equal to the dimension of the cohomology that you're interested in. Associated to then a family of Hodge structures over the punctured disk, there's a limiting mixed Hodge structure. And the limiting mixed Hodge structure is the thing that was defined before. The weight filtration comes out of monodromy, and the limiting Hodge filtration comes out of analysis, really. This was proved by Schmidt. And I think I won't get into this. I won't get into that. For algebraic curves, so these, what I'm putting up now, are, let's look at the case where you have non-trivial monodromy. So the Hodge structure is really degenerating. For curves, the way that the Hodge structures degenerate, you start with a Riemann surface of genus G, you pinch a handle, the genus of the desingularization drops by 1, pinch 2 handles, it drops by 2. It's that picture of the genus 2 curves that I put up earlier. Hodge theoretically, this is the picture that's drawn. No singularities, 1 double point, and so on, up to G double points. So that's how the limiting mixed Hodge structures get organized for weight 1, for Riemann surfaces. For algebraic surfaces, the first case, non-classical, you come to, this is how you organize the possible limiting mixed Hodge structures. So it shows one of the features that is characteristic in the non-classical case, that the Hodge theoretic stratification of limiting mixed Hodge structures is no longer linear. It's transitive, but that's only for weight 2. Once you get to weight 3, it's not linear and it's not transitive. So if you want to do, for example, how Calabi-Yaos of dimension 3 degenerate, the boundary structure is going to reflect the fact that the Hodge structure the ways the Hodge structures can degenerate is not linear, and it's not transitive. You can degenerate this way, and you don't get the same thing. And I think I won't get into that. So what those overheads that I skipped over is the following question. Let's suppose we have a family of algebraic surfaces over the disk with non-Gorenstein singularity over the origin. Smooth outside the origin, but non-Gorenstein over the origin. As I said before, it's a theorem then that monodromy is finite. Okay? So you got a singular surface, but of nice Hodge structure. You want to be able to compute the differential to first order of what happens when you move off that singular surface. In the space of Hodge structures, that's perfectly smooth, so it makes sense. You got a point, and you've got a curve. You want to know what the tangent to that curve in the space of Hodge structures is, and be able to compute it algebra geometrically. You want to then use that information to go back and say, okay, for that non-Gorenstein singularity, it has to have certain properties reflected in the Hodge theory. So you got to have a formula for the derivative of how the Hodge structure smooths, how the Hodge structure varies to first order when you smooth the surface. That's what that overhead gave formula for. So the general results, some of these have been mentioned before. You have a KSBA moduli space for a class, say, of surfaces with its canonical completion. You have the period map associates to each smooth surface its polarized Hodge structure. That sits in a quotient of the space of Hodge structures by the monodromy group, the global monodromy group. The reason you put global monodromy group is that when you have a global family of smooth varieties, to identify the cohomology of two fibers, you've got to choose a path to go from one to the other, and as you move along the path, then the cohomology groups remain isomorphic to a fixed vector space. If you choose a different path, you get the action of monodromy. It's the action of the fundamental group of the base on the cohomology of the fiber that you get by just moving cycles around closed loops. So if you're going to look at the global period mapping, you have to factor by the monodromy group. It's like taking a Riemann surface of genus 1. Its period is a point in the upper half plane, but it's only defined up to SL2Z because it depended on choosing a homology basis to integrate your differentials over. So that's the general sort of picture. So it was known classically that this mapping is, the image is a compact analytic variety. I should mention that what about these D by gammas? Classically, one used automorphic forms, things like that, to study them. Okay? In the non-classical case, in the classical case, when D is Hermitian symmetric, this D by gamma is a quasi-projective algebraic variety, and in fact it has a lot of rational functions or meromorphic functions on it that are given by ratios of automorphic forms of the same weight. It has a lot of global function theory. In the non-classical case, this D by gamma has no non-constant functions. So one is looking at quite a different, Hodge theoretically, story than in the classical case. So it was known that this is a locally closed analytic variety, and it was just recently proved by Baker, Bruno Hobby, and Tasimaran that it has an algebraic structure. It's a very interesting argument. It uses model theory from logic. And they have what they call so-called O minimal model structures, which allow them to prove, in this case, that this Hodge theoretically defined analytic object has an algebraic structure. Something quite new, it just happened within the last couple of years, and I think it's going to have should have a lot of applications of things that we have not been able to get at before. So it's known that that thing is quasi-projective. The first main result, and the quotations here, is that the thing is not, as I said before, not completed, is that this thing should have a canonical completion, and over which the so-called Hodge line bundle is ample. It's been proved in some cases, for example, if the dimension of M is 2 or 3 and so on, but the complete proof has not been done. One knows what it is as a set. So one is looking at this family, it's a space of Hodge structures. These, in the limit, will be mixed Hodge structures. Do you remember that a mixed Hodge structure is a successive extensions of pure Hodge structures? So it's something like upper triangular matrices, the blocks along the diagonal are pure Hodge structures, and extension data is the stuff above the diagonal. Taking the associated graded just means to look at the successive quotients, the blocks along the diagonal. This P bar is the associated graded polarized Hodge structures to the limiting mixed Hodge structures. So what it means is that you go to the limit, you get a limiting mixed Hodge structure, throw out the extension data. That's the minimal amount of information, if you like, that you can usefully, I think, consider in the limit. In the classical case, this was the Bailey-Borel-Satake compactification of abelian varieties in K3s. So that's what this thing is as a set. And the first result, real result, is that the period mapping, well, there are two parts to it. First is that if you look at the compactified moduli space, you look at that part of it where the local monodromies are finite. Then the result is that the period map extends across those. So you still stay in D by gamma. This is what I mentioned before. If you have finite monodromy, even though the variety becomes singular, the Hodge structure doesn't. And so the general result, which was also mentioned before, is non-Gorenstein singularities have finite monodromy. And this explains why it is true. If you go back and look at the list of singularities that occur, if you look at the non-Gorenstein ones, they're all rational singular points. And it's a fairly easy result that if the singularity that you acquire is rational, you don't lose any Hodge theory. Nothing goes to infinity in the limit. Okay. Geometrically, or to an analyst, you would say, why is that? Your variety is becoming singular. It's acquiring a singular point. You blow up the singular point. A rational singularity means that singular point, when you resolve it, is a bunch of Riemann spheres. It's like a cycle of P1s. Holomorphic differential in the limit would acquire logarithmic singularity upstairs. And you take the residue, you're going to get the residue of that holomorphic 2 form with a pole on P1 that could have only two further poles where it meets other P1s. Okay? And you have a global closed cycle. The sum of the residues being 0 means that in the limit, those holomorphic differentials cannot acquire a pole at all. That's why the geometric genus doesn't drop when you have a rational singularity. It's because the resolution is a cycle of P1s. There are other isolated singularities that can occur, interesting ones, very beautiful ones. I'm not going to get that much into those, but elliptic singularities. That's where the surface acquires an isolated singular point whose resolution is an elliptic curve. And a sort of degenerate form of that is the isolated singularity as a cusp. Just like an elliptic curve, cubic curve can degenerate into a cusp. That sort of thing happens in singularities. So Hodge theory tells you how many elliptic singularities you can have. It's very interesting. It gives a bound from below and above, and it tells you how many cusps you can have. This is quite different than the canonical singularities on a surface. Canonical singularities, the simplest one I mentioned was just an ordinary node, a double point. It's like the vertex of a cone. It's not known how many of those you can have. Even for smooth surfaces in projective 3 space, there are rough bounds, but nobody knows a good bound on how many of those you can have. But once you get elliptic singularities or cusps, then there are these good bounds, and these are realized in examples. I think the way I think of that is when you acquire these canonical singularities, Hodge theory doesn't really tell you much. The resolution is not a cycle of P1s, it's a Dinkin diagram of P1s. And you don't know how to bound the size of that Dinkin diagram. That's basically what the problem is. I'll skip that. So I want to talk a little bit about the last few minutes about this particular surface. So an eye surface is a connected, reduced surface of general type that satisfies these conditions. This is, k squared is always positive, so that's the smallest it can be. Chi of O, this means it's regular. So chi of O being 3 means that H2 of O, didn't have relations, you know what the relation would be, so it tells you how many relations there are, and you can build it up that way. That's the postulated form, and the Florentine ones have that postulated form. That means that they're pluricanonical, that they're pluricanonical, that their canonical images are easy to study. So the canonical map is a map, the rational map P1 is a pencil of genus 2 curves. As I said, the eye surfaces look in many ways like curves of genus 2. So the canonical series is a pencil of genus 2 curves. The bicanonical map is a 2-to-1 covering over this weighted projective space. The weighted projective space is just a singular cone in P3. It's a cone with one singular point of vertex. And it's 2-to-1 branched over 20. That's the surface of degree 5 in P3, not passing through the vertex and branched over the vertex. That's what should happen, because if you look along a line on this cone, take the inverse image, you're going to get a curve that's 2-to-1 over the line with 5 branch points out here and 1 branch point here. That's 6 branch points. That's a genus 2 curve. So that's the canonical series. And you can then figure out the equation of the surface in a weighted projective space. So x0, x1 have weight 1, y has weight 2, z has weight 5. This is its equation. So one knows, well, you can hold these surfaces in your hand, so to speak, at least their equations. The local Torelli property, in general means that the Hodge structure captures the moduli. That is, the mapping from moduli to the space of Hodge structures is locally 1-to-1. That's the local Torelli theorem. I should have said in the beginning that the curve, there's a global Torelli theorem that the smooth curve of genus G is uniquely determined by its Hodge structure. There are a bunch of other varieties where this is true. There's an even much larger class where it's generically determined by its Hodge structure. For example, any smooth hypersurface in projective space with about 6 exceptions on the degree has a global Torelli property. So it's suspected, but not yet proved, that global Torelli works for this surface. It's also suspected that it's proof that the global monochromic group is an arithmetic group, but whether it's the full possible arithmetic group, as big as it can be, is not known. The period domain has dimension 57, and the overheads that I went through earlier didn't leave up, dealt with what's called the infinitesimal period relation. That's the differential constraint on what happens to the Hodge structure as the surface varies. What it says is that, except in the classical case, any family of varieties, their Hodge structures satisfy a non-trivial set of differential equations. For the I surface, it's a contact system, a 57-dimensional manifold, a contact structure, and this P is basically the moduli space as a contact submanifold. There are 3 known divisors on the moduli space. The Hodge line bundle. The Hodge line bundle is the one whose fiber over each point is the highest exterior power of the space of holomorphic differentials on the fiber. It's the standard line bundle that comes with any family of algebraic varieties from Hodge theory. The locus of surfaces having a node in E1s, and then there's the locus of surfaces, these are the interesting ones, having this 1/4-1/1 singularity. It's not known whether this is the basis for pick of this. This would be be a very nice global theorem. Sort of like one knows what the pick of mg bar is. Two generators, the Hodge line bundle and nodal curve. This would be the analog. So I want to close with just a few words about Hodge theory and moduli in the non-Gorenstein case. The A1 singularities, I mentioned those earlier, and I think I won't say much about that. bottom line is that in the moduli space of surfaces, those with an A1 singularity can be detected Hodge theoretically. So the first thing that happens is that their Hodge structure, since it has an A1 singularity, remains a Hodge structure. The second thing that happens is that Hodge structure picks up an extra Hodge class. That's an extra line bundle in the surface case. And the third thing that happens here is that the line bundle has a section. The numerics tell you that section is a P1 with self-intersection -2. It contracts to an ordinary double point. And then the business about the differential of the period math tells you you get a smooth hypersurfacing moduli when you have an A1 singularity. I mean, this is something that's sort of everybody knew was more or less true, and this gives them a proof of it. The wall singularity, that's a different matter. I should say that monodromy for the A1 singularity is a finite order 2. It's a Picard-Lachance transformation. It's a Z2. This wall singularity has no monodromy. So even though the surface has this quotient singularity, you can't detect it by monodromy. So how can you detect it by Hodge theory? Well, you've got to show that something in the Hodge structure, and the Hodge structure is uniquely determined by this family over the puncture disc. You've got to show that something in the Hodge structure allows you geometrically to say this is in this case, an I surface with a wall singular point. So the way geometrically this happens, if you remember that this surface arose as a 2-to-1 covering of the cone, branch on a quintic, and the vertex. That's the smooth one. As the quintic moves into the vertex transversely, that's when the surface acquires a wall singularity. And one can describe how you desingularize the thing. So the blow up at a base point gives you a morphism, and so on. This is sort of a picture of what happens when you take the general member of it. Well, let me back up just a second. So we have this wall surface with a singularity, and we allow the quintic to pass through the vertex, otherwise it's general, and you desingularize the limit by this construction here. You blow up the vertex, and then you desingularize that limit surface. So one can say what the singularities are that you put in the origin. I think I won't go through these pictures until I'm going to run out of time. I want to just give the bottom line of the story. So the desingularization is an elliptic surface. You haven't lost any of your holomorphic differentials. In the limit, because you have, it's a general fact that if you have finite monodromy, you don't lose any of your holomorphic differentials in the limit. Even though the surface becomes singular, those holomorphic two forms in the limit remain holomorphic. So in the limit, you get an elliptic surface with PG equals 2, and it has a bisection coming out of blowing up that singular point. The dimension of the space of elliptic surfaces with these numerics is 28. I'm sorry, the dimension of the space of I surfaces, the moduli space, is 28. It's a compact submanifold. The number of moduli of this elliptic surface is 32. Keeping the line bundle that comes from this bisection, the thing that contracts to the singular point, keeping the line bundles two conditions. If you're under the left Schatz 1-1 theorem, the number of conditions for a cohomology class to be a Hodge class of a line bundle is generally equal to the PG of the surface. Not always, but that's an upper bound. In this case, it's realized. So to keep this line bundle, you lose two moduli. But you don't have a section. To keep the section, you have to impose one further condition. Once you keep that section, that then becomes a curve that can be contracted, and that's then an I surface with a wall singularity. So sitting in the boundary of the moduli of I surfaces, 28-dimensional guy, you have a 27-parameter family of these wall singular surfaces, whose resolutions then are elliptic surfaces with a bifurcation. And to actually prove all this, you have to do some standard cohomology, but the crucial point is to compute the derivative of the Hodge structure at the origin. So surface is singular, you smooth it to first order and see what happens from the Hodge theory. And what you find is exactly this structure. At first, the curve disappears in one direction, and then the line bundle disappears in two more directions. I'll just close with the non-Gorenstein case. The non-Gorenstein normal surfaces will have either elliptic singularities or cusps. And these are these types that I mentioned when I showed you that diagram of how Hodge structures degenerate. There were 5 types. The subscript means each number is an elliptic singularity, and this is the degree. So what Hodge theory tells you is that these are the possibilities. And then, knowing what these possibilities are, you go back over and say, well, what can the surfaces be? And this is the list. You've got an Griffiths surface and a couple of rule surfaces. And then there's some other analysis about how you desingularize the module I won't get into. But this is the sort of diagram that one wants. Here you have the Hodge theory, and this is Hodge theoretic stuff over here also. And that allows you to fill in dimensions and what the surfaces are. And that's the kind of picture that one would like to get, to be able to use Hodge theory for aesthetic moduli of at least some surfaces. Those are the references. Okay. Thank you.
Are there any questions?
Sure.
So, for the case of curves, when you have a complicated singularity and you map it to the moduli space, then you have the puncture disk gets mapped to the smooth part of the moduli, and then the singular point, when it arrives at infinity, it contains several irreducible components. Right? So, in the case of surfaces, can one detect using Hodge theory if this compactified smoothing is going to be irreducible?
Yeah, very good question. The one reducible I surface is when you take this double plane over this cone and you let the branch curve degenerate into a double, twice infinity plus something. And then the surface will, so on the limit, the canonical bundle is 2 Gorenstein, but not Gorenstein. The surface will separate into 2
del Pezzo's moving along a rather specific curve. So Hodge theory, the derivative of a period map at that limit gives you a guess. It doesn't, it just says, oh, this smells like del Pezzo with this type of curve on it. So I think the way I think of it is that the Hodge theory is a guide, not an answer. You have to put the algebra and geometric arguments in to get the answer. Yeah.
In this case of high surfaces, if you construct the graded tree, canonical graded tree for all the types, you list some types. One, which is the generic one, the moduli space, dimension 28, and so on. There should be another canonical rings for this 22 dimension, and so on. If you construct those rings and you prove that you can put them together into a family, a flat family, and that family remains the same, and you can say, okay, in the special fiber in this case, and then I move out, and I can prove I get the general case. Can I conclude that this singular fiber is has singularities of these types you listed, cyclic quotient, Q Lorentz times multiple, and so on? Is that enough? Obviously, in one direction is clear.
I think that the eye surface is not proved, but that should be enough. You're going to need some sort of local Torelli properties that the Hodge theory is not losing information. There are a few surfaces, like the Keymass surfaces, where PG is 1, K squared is 1, and so in this case, the space of Hodge structures is like K3s, and in fact, the Keynote surfaces are constructed from K3s with some declaration of K3s. And they were rigged up in such a way that at least the Hodge theory, as far as the limiting mixed Hodge structures go, will not show up, won't protect that. Whether the more refined notion where you look at what are called these Mumford subdomains, where you have Hodge structures with additional symmetries, or Hodge tensors in the generic form. That could, in general, tell you something. But you do need some sort of, I think, local Torelli type of property of the surfaces.
I think that's definitely enough if you increase the BG and K squared.
Correct.
So, who knows?
I mean, there's this wonderful paper by Robbie DePeel, Murphy's Law.
Yes.
And he says that if you look at moduli of surfaces of general type, think of anything that can go wrong on an algebraic scheme. Components, singularities, non-reduced everywhere, multiple components. Think of the worst possible thing that can happen through a scheme. That can be realized by the moduli of a surface of general type. So the story is not going to be like it is for curves. It's just like, in the wonderful book by Griffiths and Castellovo on surfaces, they said, well, surfaces, algebraic curves are this beautiful coherent theory where all of the curves of different genera hang together in this beautiful structure and so on. Algebraic surfaces are like a botanical garden, and you have these beautiful plants that you study one at a time. And I think some of that flavor of surfaces has to come into this.
Any more questions? I think this could be